Dr. D here, and today we're going to learn about some periodic trends and why they occur. We'll predominantly focus on atomic size and the electrostatic effects that caused it, but we'll also lightly discuss ionization energy as well. So let's dive into it in Content with Content. So one of the first periodic trends we're going to talk about is atomic size. And the overall rule for atomic size is as we go down the periodic table, we're going to increase in atomic size. And this is going to be the larger of the two effects. And as we go from right to left, we're also going to increase in atomic size, but this is the lesser of the two effects. So why does this occur? Well, to help explain this, we're going to talk about electrostatic effects. And the first one we're going to talk about is nuclear charge. And this is when we have opposite charges attracting each other. So if we have higher charges, they're going to interact more than if we have lower charges. So for instance, let's say we have a hydrogen atom, where we're going to have a nucleus, and that's going to contain one proton, and then we have the electron surrounding it in the 1s orbital. And we're going to compare that with a helium cation. So all we're doing is just adding one more proton. That's going to pull the electron closer to the nucleus because of this additional proton, creating a higher charge. The next electrostatic effect we're going to talk about is going to be shielding effects. And this essentially occurs from like charges repelling each other. So if we have two electrons, they don't want to be that close to each other, so they're going to actually repel one another. And this is essentially the premise behind shielding effects. So the first one we're going to talk about is shielding from core electrons, or the inner electrons. And this is going to have a very large effect. So if we have hydrogen, and we compare that with, say, lithium, for lithium, we're on the second row now, so now we have a 2s orbital, and basically that outer electron, that valence electron, is going to be shielded or blocked from accessing that positive charge of the nucleus as well as it could because of these core electrons, or inner electrons. And then we can have another shielding effect caused from shielding from electrons on the same energy level. So if we compare lithium with, say, lithium minus, we are going to have an extra electron in here, and this is going to be spread out just a little bit wider, or a little bit larger atomic radius than neutral lithium, because we have a repulsion from the electron in the same energy level, shown here. And so this is going to be a much smaller effect compared to the shielding from the core electrons. And then for our next electrostatic effect, I want to kind of discuss a little bit about the general shapes of orbitals. So we're going to start with a 1s orbital, and we can map out the probability of the electron density compared to the distance from nucleus, shown here. And then we'll do the same for a 2s orbital, and for also a 3s orbital. Now, on these, you might notice that we have some peaks or maxima, and this is where we have a higher probability of electron density. So this is where the electrons are going to spend majority of their time. And then you may also notice for the 2s and 3s orbitals, we have this spot where it essentially goes down, where the probability goes down to 0. And these troughs or nodes are where we have a 0 probability of electron density, which is a little weird if you really sit down and think about it. We can have an electron existing in one region for a portion of time, and then it can also exist in one of those other regions for a portion of time without passing through the area in between. So it's a little difficult to wrap your head around, but to be honest, quantum mechanics has some very weird phenomena that occur that we don't normally see in our everyday lives. So with this in mind, I want to kind of focus in on this kind of smaller region on this 2s orbital. And so we're going to go ahead and essentially make an overlay of the 1s and 2s orbital to help illustrate this next effect, which is penetration. So if we look at our 1s orbital, we'll see that it's a certain distance from the nucleus. And then if we map on the 2s orbital, we'll see that we have the same thing, but that smaller region that we talked about earlier actually goes into or penetrates the 1s orbital region. And that's going to cause two things to occur. That's going to increase the nuclear attraction because now that electron spends some time a little bit closer to the nucleus. And it's also going to decrease the shielding effect because now it's actually getting past the 1s orbit, or the electrons in the 1s orbital, which would prevent it from experiencing the full effect of the nuclear charge. And so this is what penetration is and why it generates some kind of unusual effects. So we went through 3 electrostatic effects. Nuclear charge, where we have opposite charges attracting one another. We have shielding effects caused from like charges repelling each other, so the electrons will repel one another. And then we have penetration, which essentially alters things just a little bit, where we're going to increase the nuclear charge and decrease the shielding effects. So going back and looking at our periodic table, we can see that we have an increasing energy level will greatly increase our atomic size, and this is, again, mainly due to shielding effects from those core electrons. So if we look at hydrogen, we'll have our 1s orbital. If we have lithium, we'll have a 2s orbital, which is much larger in size. And then we'll have sodium, which is a 3s orbital, which is even greater in size. And so again, this is largely due from the shielding effects. And then if we look at our periodic table again, and as we are increasing our number of protons, so as we're going from left to right, we're going to be decreasing the atomic size mainly because of the effective nuclear charge. So the amount of charge an electron experiences from the nucleus. So we're going to look at lithium here and compare that with, say, boron. And in this case, we have two competing effects. We have a little bit of shielding occurring from the electron being in the same energy level, but this is a much, much smaller effect compared to the more overpowering effect of increasing the number of protons, or increasing the effective nuclear charge. And so that's still going to contract the electrons to be closer to the nucleus, making the overall atomic size smaller. And we can see this continues on for oxygen as well, for where now we're adding even more protons, and so that's going to confine these electrons to be in a much smaller region, or a region closer to the nucleus. So another periodic trend I want to talk about is the first ionization energy. And this is the amount of energy it takes to remove an electron from an atom. Or specifically for first ionization energy, this is the energy required to remove the first electron from a neutral element. And for the most part, this is inversely related to the atomic size. Now there's going to be some exceptions, but this is the general rule that you can kind of go by. So here's a table with the first ionization energies for various elements. And one of the things that we'll notice is that kind of at the peaks of each of these, we have our noble gases. And within any row, the noble gas will be the thing that requires the most energy to remove an electron from. And we'll also notice that the very first element on any given row typically has the lowest ionization energy. All right, so again, it follows atomic size for the most part. There's a few things I do want to kind of point out. So if we look at the fourth element, beryllium, and the fifth element, boron, we'll see that boron has a little bit lower ionization energy than beryllium. And the main reason for this is because when we are looking at boron, this is when an electron is going to go into the 2p orbital. It's the very first one. And so that electron that falls in the 2p orbital is a little bit easier to remove, mainly because of shielding effects from the 2s orbitals undergoing penetration. So that's going to cause a little bit more shielding that's similar to those shielding from a core electron. So that's why it's a little bit easier to remove. And then another one I want to focus on is the seventh element, nitrogen, and the eighth element, oxygen, where again, we're not quite following the trend. And to help illustrate this a little bit, I'm going to pull up the orbital diagrams of nitrogen, where we fill up our 1s orbital, our 2s orbital, and our 2p orbital. And then we're going to pull up the orbital diagram for oxygen. And it's very, very similar, with the main exception being that now we're adding in another electron into the 2p orbital, but this time it has to have an opposite spin. And so what this does is this actually causes something that's called spin-spin repulsion. So whenever you add in another electron into the same orbital, it has to have a different spin. And this kind of repulsion is going to be amplified even more because we have a couple other electrons in the other p orbitals. And so this is kind of like one of the main reasons why Hund's rule actually remains true. The energy it takes to add in another electron with opposite spin is a little bit higher. And because of that, it's a little less stable, and so it's going to be easier to remove that electron because that repulsion is just a little bit higher. And so this kind of explains the first ionization trends here. For the most part, it follows atomic size. So the smaller the atom, the harder it is to remove that electron. But we also have a few exceptions where you have to think about how the electrons are oriented around what orbitals they are in. So kind of keep that in mind as well if you come up with any exceptions. So to kind of summarize what we've learned today, as we go down the periodic table, we're going to increase in atomic size, and this is the larger effect. As we go from right to left, we're going to also increase in atomic size, but this is the smaller effect. And then as we go from bottom to top, we're going to increase in first ionization energy. And as we go from left to right, we're going to increase in first ionization energy. So that's all I have for you guys today. I hope you felt like you learned something. And as always, keep thinking, and I'll see you next time. Goodbye!